Here's a famous question. How many people need to be in a room before the chance that at least two of them share a birthday exceeds 50%? What's your guess? Maybe 100, maybe 150, maybe all 365 as days of the year? Well, the answer is actually 23 people. And if you're like me, that's quite unexpected. This is called the birthday paradox, and it's really a surprise, not a paradox, but it highlights that what we think of as probability is sometimes quite counterintuitive. Remember, probability is a tool scientists use to predict the future. It is a model that often gives accurate and applicable results that describe the likelihood of events in the world. However, when this model brings up counterintuitive results, like in this birthday problem, we naturally question it. And it is then a mathematician's job to resolve those questions by making a rigorous foundation on axioms. And in probability, there are exactly three axioms that make everything rigorous. In this video, I want you to learn and understand these rules. But to do that, we first need to define a couple of terms. Let's use a familiar example, a six-sided die. When you roll it, what are the possible outcomes? Well, of course, you could either roll a 1, 2, 3, 4, 5, or 6. This set of outcomes is called the sample space of an experiment. Following that, consider any set formed with some elements of the sample space, such as these. These are called events. It is meaningful to then ask about the probability of an event, which should give a number to our intuitive expectation that an event would occur. For example, taking this event 1, 2, 3 from our sample space, we are interested in its probability, which in language would translate to, upon rolling a die, what is the chance of getting a 1, a 2, or a 3. In general, in any process where there is randomness, we can define a sample space, which is a set of outcomes, and then ask what is the chance that we get a specific set of outcomes from this process, or an event. Now we are ready to define the probability axioms. Remember, axioms are minimal assumptions. They are rules so basic that they seem unavoidable. It is always necessary to make some assumptions in order to get any conclusions. And if you deny all assumptions entirely, well, you're a nihilist, and no one wants to talk to you. So in 1933, mathematician Andrei Kolmogorov defined three axioms that make up all of probability theory. First axiom: the probability of an event is non-negative. This makes a lot of sense. We can't talk about a negative 10% chance of something, for example. Second axiom: the probability of the sample space is 1. This means that whenever we conduct a random process, we must get at least some outcome. For example, about the weather. Tomorrow there will be weather. I don't care if it's rainy or sunny. With probability 1, there will be weather tomorrow. And that's what this second axiom means. Also makes a lot of sense. Now the third axiom, get ready for this one. If two events cannot occur at the same time, then the probability of either one happening is the sum of the probabilities of them individually happening. Now what does that mean? This one is the trickiest but the most powerful. Let's look at our dice example again. Take the event of rolling a 1, call it A. Take the event of rolling a 2, call it B. You cannot roll a 1 and a 2 at the same time, and you should remember we call such events mutually exclusive. So the probability that A or B happens is equal to the sum of the individual probabilities of A and of B. And that is in essence the third axiom. Here it is in proper mathematical symbols for those interested. And that is it. Can you imagine that just from these three axioms we can rigorously prove every result in probability theory? To end this video, I'll show you two examples of such theorems. Let's now prove, using these three axioms, that the probability of the empty set is 0. Remember, the empty set is a set with nothing in it, and by virtue of the axiom it makes sense that this will be impossible, or a probability 0. So, to do this, let's note first that the union of an event A, we're just going to use A as some event, the union of A with the empty set is still A, right? Taking A, giving it every element in the empty set, which is nothing, we still get the same set. Cool. The second thing we note is that the intersection of A and the empty set is of course the empty set. What element is common to both nothing and to some A? That is also nothing. So then we can use the third axiom. We know that A and the empty set are both sets, such that their intersection is empty, and so we know that the probability of their union is the sum of the individual probabilities, but their union is equal to A. So the probability of their union, which is P of A, is the sum of P of A and P of empty set. And from this, we simply subtract P of A from both sides, and of course get that P of the empty set is 0. Very simple, using our 3 axioms, in fact, 1 and 3. Finally, we'll prove that for two events A and B, if B is a subset of A, this symbol means subset, then the probability of B is no more than the probability of A. Remember, a subset is a set that has all the same elements as another set within it. So here's a helpful diagram. There's the sample space S, then there's some event A in it, and also B that's contained within A, as written here. So we'll prove this by decomposing A into two mutually exclusive events, then using the third axiom. So note that A as a union of mutually exclusive events, well, it's simply the union of B and this part, that is all of A, but not B. So how do we write that? I just said the union of B and all that is A, but not B. So we intersect A with not B. It's clear that these are mutually exclusive, or their intersection is empty. So we can apply the third axiom and see that the probability of A is equal to the probability of this, which is simply the sum of the individual probabilities, P of B and P of A intersect not B. But using the first axiom, we know that the probability of this event, because it's still an event, is non-negative. So we know that P of A intersect not B is greater than 0. From that, we obviously get that P of A minus P of B is not 0, or greater than 0, I mean, like this, because we simply, this is equal to P of A minus P of B from this inequality. And then we, of course, get that P of A is greater than or equal to P of B as needed. And we are done with the theorem. And that is it. See you next time.